Hello everybody, this is Dr. Christopher White, and in today's video we are going to be continuing with rocks. So this is rocks part 2. Okay, so we're going to be looking at sedimentary rocks. Now sedimentary rocks are important for historical geology because they are the only class of rock that tells us what was going on the surface of the earth at a given location at a given time. So sedimentary rocks are a reflection of the source of the sediment, how that sediment was transported, and the environment into which that sediment was deposited. So all of those different factors will be combined together to form a distinct sedimentary unit. And as a geologist, one of the jobs you can have is to come along and you can try and interpret those sedimentary rocks to work out, what was the environment at this location. So for instance, we can use sedimentary rocks and we can say, well, for Houston, maybe 400 million years ago, Houston was maybe part of a desert or a shallow, warm ocean, or maybe it was part of a fast-flowing mountain river system. All of that information is contained within sedimentary rocks. Now, igneous and metamorphic rocks are great if you want to know what's happening subsurface, because that's where most igneous and metamorphic processes occur. Sedimentary rocks, on the other hand, are just about what was happening on the surface of the earth. So if you want to know, right, what was the environment like, what was happening in this area, the animals in this area, what kind of environment were they experiencing, then only sedimentary rocks can give you that information. So sedimentary rocks fall into three groups: the clastic, the carbonate, and the chemical. So clastic sedimentary rocks consist of clasts. So a clast is a fragment of a rock or a mineral, which essentially are then cemented together to give you a clastic sedimentary rock. So something like a sandstone is a good example of a clastic rock. Next we have the carbonate sedimentary rocks. As the name suggests, those are rocks which are dominated by carbonate minerals. Calcite is the most common, but you can also have carbonate rocks which are dominated by dolomite and aragonite. And most carbonate rocks are the result of calcium carbonate or another carbonate mineral being deposited due to some biogenic process. So something like an animal shell, for instance. And the final type of sedimentary rock are the chemical sedimentary rocks. Now these are sedimentary rocks that consist of minerals deposited due to evaporation. So they're the evaporite minerals and evaporite rocks. Or rocks which are, minerals which are deposited directly from ambient, so essentially surface temperature, or hydrothermal waters. So we have these three different types of rock. Now clastic rocks are the ones that we're going to come across most of the time, because carbonate and chemical sedimentary rocks, they tend to have a far more limited scope for formation, so you don't get them anywhere near as widely. Okay, so clastic sedimentary rocks. As said, clastic sedimentary rocks consist of clasts, which are fragments of pre-existing rocks or minerals. Now the rocks or the minerals can have come from an igneous rock, a metamorphic rock, or a sedimentary rock. And these clasts will be cemented together and held in place to form a rock, or these sediments can be incorporated into what we also refer to as the matrix. Either way, that's just the process of taking that sediment, holding it all together in place, and essentially liquefying it to make a cohesive rock. So sediments form as the result of the action of water, wind, ice, chemical reactions, or gravity. Now, the vast majority of clastic sedimentary rocks are related to water processes because there's just so much of it moving around on the surface of the earth. Sediments are often transported, during which time the shape of the clasts and the composition of the sediment itself will change. Now this is very, very important, because as a geologist what we'll do is we'll look at the clasts, we'll look at what the clasts are made of, and we'll say, right, is this sediment I'm looking at a mature clastic sediment or a immature clastic sediment? The difference is how long was the sediment transported for. So typically a mature clastic sediment will be transported for very, very long distances. That means the clasts are going to have lots and lots of time to be reworked. And so that means the sediment you get is a reflection of that long transport time, but it also tells you the sediment and the rock that formed from it was deposited a very long way from the sediment source. In contrast, an immature sediment will be deposited very close to the sediment source. Now this means that the sediment won't have a won't have a lot of time to be reworked, and so we can see that when we look at the clasts. We can see they have certain features like how angular they are, and that gives us a good indication of, this sediment hasn't been transported very far, so this is an immature sediment. And so, we'll be looking for this kind of information when we look at our sedimentary rocks. Now, clastic sediments, or should I say class sizes, are put into 4 broad groups. So they are clays, silts, sands and gravels. So a clay is anything that's less than 0.004 millimeters. So a clay size clast is not visible to the naked eye. Now you can tell it's a clay size clast because what you can do is you can actually flake off a little piece of the rock. You can chew that little flake and you'll produce a powder in your mouth, and when you rub that powder against the roof of your mouth, if it's a clay, it will produce a very kind of silky feel. The next class size is a silt. That's between 0.004 and 0.62 millimeters in diameter. Once again, those grains are also invisible, but if you take a flake of a silt-dominated sedimentary rock and you chew that little flake and then you rub the resulting paste on the roof of your mouth, you'll get something that feels a little coarser. So the way to tell the difference between clay-sized clasts and silt-sized clasts is to eat a bit of rock. Yeah, but it's effective. What can I say? Now, in terms of actually being able to see the clasts, you're not really going to be able to start seeing the clasts until you are in the sand sized class size. So that's between 0.062 and 2 millimeters in diameter. Now sand class dominated rocks, when you rub your finger over them, you can actually feel the class because the rock itself feels like a piece of sandpaper. So that's one of the ways you can also tell that the class size is getting larger, because clay dominated rocks will feel very smooth. Silt dominated rocks will also feel quite smooth. Sand dominated rocks, on the other hand, you'll really be able to feel that rough sandpaper like texture. And the final broad class of class sizes are the gravels, and that's anything greater than 2 millimeters, and in that instance the clasts are easily visible to the naked eye. Now this is a very simple classification scheme. The one that's normally used by geologists is this one. This is the Wentworth classification scheme, and you can see it's a little bit more complicated. Now we're going to ignore colloid down here. So it goes from clay, silt, very fine sand, medium, coarse, very coarse. Then we're into the gravels, very fine gravel, medium, coarse, very coarse gravel. Then we have cobbles, and finally boulders. Boulder is the largest of the class sizes. And you can see they are all given diameters in millimeters. Obviously when we're down into the very fine portion, we start to give them diameters in microns, which are of course fractions of a millimeter. So this is what was very commonly used. Now in order to tell the difference, once again, you can't see clays and silts when you look at the rock, so you have to chew the rock in order to work out, is it a silt, is it a clay? When it comes to the sands, well, it can actually be quite difficult to see some of these smaller sand sizes. So one of the easiest ways of actually working out how coarse the sand is using your sense of touch. And so if it feels like a very fine piece of sandpaper, well, you're probably dealing with a fine or very fine sand. If it feels like a kind of medium grit sandpaper, you're dealing with a medium sand. And if it feels like quite a coarse sandpaper, you're dealing with a coarse or very coarse sand. Now, once you get into the gravels, life becomes a lot easier because you can actually see them. And so classifying the different gravel sizes is quite easy. Obviously, cobbles, very straightforward, and boulders, also very straightforward. So the reason that we go into this level of fine detail is because, once again, different sedimentary environments will produce slightly different sedimentary rocks. Okay, so you can have a sandstone that can be made of very coarse sand, you can have a sandstone made of medium sand, and you can have a sandstone made of very fine sand. And the class size, the diameter of those class, is a reflection of the environment. So it gives you a way of refining sand-based clastic sedimentary rocks even further. giving you that, even more possible detail to give you an even better idea of where that rock could have formed. So the first thing we're going to think about is class sorting. Now, sedimentary rocks are often described based on the degree of sorting, and there are two broad groups. There are well-sorted clastic sedimentary rocks and poorly sorted clastic sedimentary rocks. So a well-sorted rock is going to have quite a tight range of clast sizes, so all the clasts are going to be approximately the same diameter. In contrast, a poorly sorted sedimentary rock is going to have quite a wide range of clast sizes, so the clasts are going to have a whole mixture of different diameters. Now, typically, the better sorted your sediment is, the longer it's been transported for. So most of the time, a well-sorted clastic sediment is an indicator of a mature sedimentary rock. A poorly sorted clastic sediment is an indicator of an immature sedimentary rock, but there are other factors in play. So the degree of sorting is a mixture of the energy of the environment. So obviously, the higher the energy of the environment, the quicker and more forcefully the clasts will bang into each other. Okay, so if you think of a very fast-flowing mountain river, the clasts in that riverbed are bouncing around all over the place, they're hitting each other, and as they hit each other, they start knocking pieces off each other. And so that means big clasts will very quickly start hitting each other, start knocking chunks off each other, and big clasts will steadily get smaller and smaller and smaller. So over time, big clasts will be lost, and they'll be replaced by the fragments of those big clasts, so lots and lots of much smaller clasts made from the original larger clasts. And so over time, as the big clasts break down, your sediment naturally becomes better sorted because the bigger clasts are being removed and those larger clasts are being turned into lots of very, very small clasts. Now, the first way we can increase the rate of that process is energy. The more energetic the environment, the faster that process will take place. Not really a huge shock. There's also the duration of transport. Once again, the longer we transport our sediment for, the more time the clasts have to bang into each other and essentially knock pieces off each other. And so the longer the transport time, the more time there is for a larger class to be broken down into smaller clasts. So once again, the longer the duration of transport, the better sorted your sediment will become. And then finally, we have the abrasion factor. So over time, clasts will collide. This is a reflection of the energy and the duration of transport. And so abrasion is, very, very important because the abrasion is really what's going to control, well, the abrasion is going to be affected by the energy of the environment and the duration. And so when you have a high energy environment and very, very long transport times, the level of abrasion is going to be very, very high. And so you're going to end up with quite a well-sorted sediment because those larger clasts are going to be removed and they're going to be replaced with lots of smaller clasts. The size range is going to get a lot tighter. So if we look at these two sediments, we can see we have a couple of different situations. So here we have a nice conglomerate. Okay, you can see rounded clasts. Now, once again, if we just go back to our Wentworth classification here, you can see a lot of these clasts, the larger ones are going to be about a cobble in size. We have some finer material. If you look at it, you can see you've got, some smaller pieces in there. Those are going to be gravels. And then when you look at the matrix that these pieces of rock are sitting in, it looks kind of dusty, slightly sandy almost. This is going to be probably a sand-dominated matrix. There's probably not going to be much clay or silt in that matrix. So this is an example of quite a poorly sorted sediment because we have cobbles, we have gravels, and we have sands. That's a very, very big range of class sizes. In contrast, if we look at this sediment down here, we can see that a lot of these clasts are, give or take, about the same size. So this is a pen knife here. So you can see that a lot of these clasts are going to be somewhere in the fine to medium gravel range. So we can see that a lot of this stuff is a relatively tight size range. So this would be an example of quite a well-sorted sediment. So this rock formed from quite a poorly sorted sediment, and this rock formed from a pretty well-sorted, well, should I say this sediment is a pretty well-sorted sediment. So as geologists, this is going to give us some kind of indication of, what's going on. So for instance, if I look up here at this conglomerate, well, we can see we've got these large clasts. Well, in order to move a large clast, we clearly need quite a lot of energy, don't we? Because you've got your water or ice or whatever has to have a lot of oomph in order to get these big pieces of rock to move. So clearly we're dealing with some kind of quite high energy environment. We can see that even though the clasts are quite large, they have actually been rounded to some degree. So we know the sharp corners have been knocked off them as well. So that means they've been transported for a while, which means the abrasion has actually been quite high. So we haven't got, very angular pieces of rock, but we have a relatively well-rounded pieces of rock. Now, at the other end of the scale, actually compare it to this sediment down here. You can see a lot of these clasts actually have quite angular corners to them, which would imply the sediment hasn't been transported very far. We can also see that, although it's quite well sorted, the clasts themselves aren't that large, so the environment probably wouldn't have been too high energy. So we're just looking at these, a few general factors, and you're kind of already getting a bit of a feel as to what the possible environment could have been like. This was probably quite a high energy environment, and the duration of transport was probably relatively long, so maybe something like a mountain river system. Now this one's a little bit more complicated because we have got an angular sediment, which would imply, not the sediment hasn't been transported very far, but the sediment is also quite well sorted, which would imply it's been transported for a little while. So this particular sediment here is actually a little bit of an enigma, in that it has, two obvious features which would appear to be contradictory. So speaking of the shape of the clasts, this brings us on to clast rounding. Now, clasts are typically typically classified as either rounded, sub-rounded, or angular. You can see them highlighted here in green, blue, and orange. So rounding is defined as how close a clast is to a perfect sphere or elliptical shape. So the more rounded your clast is, the closer it will get to a nice smooth ellipse or sphere. Okay, so a rounded clast will have all the corners rounded off, so you'll have a nice smooth looking clast. So these are reasonably nice examples of rounded clasts. You can see nice rounded corners all around here. The next grade down is the sub-rounded clast. Now in the case of a sub-rounded clast, what we have is a clast that, yes, it has some rounded corners, like this one here for instance, but it also has some sharper corners. So we have rounded corners and sharper corners combined in one clast. And then finally we have angular clasts. These are clasts where you have pretty much nothing but sharp corners. Now we also have a couple of other different types of clast rounding, but we're not really going to worry about those too much. So the degree of rounding is once again a reflection of the length of time a sediment's being transported for, because it's going back to abrasion. So we have to think about the energy of the system and how long the sediment's been moved for. Obviously, the more high energy and the longer the distance the sediment's been transported for, the more time there is for sharp corners to be knocked off your clasts, and the better rounded they will become. So mature sediments will often have quite well-rounded clasts. Immature sediments will often have quite angular clasts. So the rounding of the clast is the result of the hardness of the clast. Obviously, if your clast is made from something quite hard, it's going to take longer to be rounded. In contrast, if your clast is made from something quite soft, it will round quite quickly. We also have the energy of the environment. The higher the energy of the environment, the faster and more violent the impacts between the clasts will be. And so you'll have lots of impacts, one after another, in very, very quick succession. And this means that sharp corners will be knocked off clasts quite quickly. And then obviously we have the duration of transport. The longer the sediment is being transported for, the more time clasts have to bang into each other, and so that means you have greater opportunities for the sharp corners to be knocked off. So that's what's going to affect the degree of rounding that we see in our clasts. Now, in terms of the clasts that actually show rounding, it's the sands, the gravels, the cobbles, and the boulders. Silts and clays are too fine, so they don't round. Only sands, gravels, cobbles, and boulders can have, indications of rounding. Now, next there is the class maturity. Now, so far we've already touched on textural maturity, how well sorted are our clasts, what's the range of class sizes, and how well rounded are our clasts. Now, those three are combined by physical things, how fast is the water, or how energetic is the system, how long has the sediment been transported for, etc. Now, the other type of maturity is called chemical maturity. So, chemical maturity is the result of how reactive are the minerals being transported. So some minerals, for instance olivine, micas, they don't get on particularly well on the surface of the earth. They break down very, very quickly, they react with water, and the mineral is very quickly destroyed. And so what happens is over time, soft minerals will be destroyed and lost from your sediment, and hard minerals will begin to become more and more important. So if you, for instance, were to have a sediment that consisted of, let's say, 50% mica and 50% quartz, obviously the longer that sediment got transported for, the more mica would be lost and destroyed, and so that would be lost from the sediment, and so over time the proportion of the quartz would get higher and higher and higher. And so this means that when you have a mature sediment that's been transported for long periods of time, a mature clastic sediment will often be quite quartz and feldspar rich, because those are the two hardest and most common minerals present within clastic sedimentary rocks. So they tend to dominate. Now, luckily they also tend to be quite chemically inert. So that means not only are they physically strong and they won't be destroyed, very quickly due to impact, but they will also not react with things like the water, and so they'll also persist for a long period of time because they're not chemically breaking down either. Another different material that is also chemically quite inert are clays. Clays are very, very chemically stable minerals, and so they can also exist quite comfortably on the surface of the earth. So over time your sediment is going to have textural maturity, so that's physical processes, so that's going to essentially round the clasts and decrease the range of class sizes, so your clasts are going to become close, the range of class sizes is going to get smaller over time. And then we're going to have chemical maturity, which is the removal of reactive minerals, and essentially as they're lost, that means any chemically more inert minerals will steadily become a larger proportion of the sediment over time. So by looking at the shape of the clasts and what the sediment is made from, we can begin to actually infer how mature is our sediment, immature or mature. And as we've already touched on, mature sediments tend to be deposited at greater distances from the sediment source, and so they're often referred to as distal sediments because they are a long way from where the sediment was formed. In contrast, immature sediments are also sometimes referred to as proximal sediments because they are typically deposited relatively close to the sediment source. Okay, so how do we split up our clastic sedimentary rocks? Well, it's actually quite straightforward. It's all to do with the size of the clasts. So, if you have a rock that is dominated by gravel, cobble or boulder size clasts, you're going to have either a breccia or a conglomerate. If you have a sedimentary rock, clastic sedimentary rock, which is dominated by sand size clasts, well, you're going to have yourself a sandstone. Now there's subgroups of sandstone, so there are a few lesser there are lesser sandstones, but the whole group in general is referred to as simply sandstones. If you have a sedimentary rock that's a mixture of both sandy sediments or sand-sized clasts and clay and silt-sized clasts, you're going to be looking at a greywacke. If your sediment is dominated by silt-sized clasts, you're going to have a siltstone. If your rock is dominated by clay-sized clasts, you're going to have yourself a shale or claystone. And if you can't really distinguish between the silt and the clay, so it's a bit, let's say your rock is like 40% silt and 60% clay, so you can't really say it's one or the other, then you'll typically refer to that rock as a mudstone. So a mudstone is a mixture of both silt and clay-sized particles. Okay, so conglomerates and breccias are going to be gravels, cobbles and boulders. Sandstones, sand-sized clasts, Grey wackies, sand-sized clasts with a good mud component, so there'll be clay and silt mixed in with the sand. Siltstones are going to be dominated by silt-sized clasts. Shales and clay stones are going to be dominated by clay-sized clasts, and if your sediment is a mixture of both silt and clay-sized clasts, you're going to simply refer to it as a mudstone. And so it's relatively simple. To classify clastic sedimentary rocks. And you know what? This is probably a great point to stop. So once again, stop the presentation, get up, have a walk around, get a glass of water, and then come back for part 2.